Really not easy. I really do. I love you. And I gained weight.
You don't know about today.
I did. I was so tired. I was like, nope, got to stop.
You got the one at the one by the hill?
I just the one that was right off the highway. Yeah, the new one. I like it.
I call that one mine.
I like that one. It's like it's right there. Just get back on. Really.
I know.
Takes a lot of my money now.
Yeah.
But when you're real tired, it works.
Yeah. Okay, so did everybody get a Valentine? The only one you got? We glad you got one. Did you take one? Yeah, you can have one of these two. You can have sweet and salt. Did you get one? So do me a favor and don't leave the wrappers. Put it right when you think. I would be very appreciative. Yeah, you need to trust it. Thank you.
Did you
not get one? Did everybody get one now? Okay.
Thank you very much.
By the way. You're welcome. Okay, because we're starting chapter 11. Okay, 11 is called Reactions of Alcohols. I want you to know that you already know some of them. That's how good you are. Okay, let's go to the next slide. Maybe today. Okay. Oh, it is also hot. I'm getting 17. I got 16. All right, I got 17. So everybody's up here, right? Yes, it's all of the above. Woohoo. Okay, so these are the types of reactions of alcohols. It's kind of an overview. Okay, the first one is dehydration. We dehydrated alcohols to make alkene. Alkene. No, you do something else to me. We're going to do this.
I still break.
Okay. You were feeling great? That's all right. Okay, do you remember what you used to dehydrate alcohol? What reagent? Because we did this last time. What does dehydration mean? Loss of
Water.
That help? Make water leave. You add acid. What acid? 2. Sulfuric or phosphoric, not HCl. Okay. Remember, you heat it up. You make a more highly substituted double bond. Remember that thing? Okay. All right. Oxidation is the one that we're going to talk about today. Making ketones and aldehydes from alcohol. Okay, oxidation is loss of hydrogen. Okay, loss of hydrogen. Okay, dehydration is loss of the whole water molecule. All right, substitution. We took alcohols and we substituted, right? That means something replaces the OH. What reagents do we do that? H what? HCl, HBr, HI. Okay, and then reduction is going from an OH to an H. You'll see there's a little trick in that. And then esterification. Did he do that in lab? Ooh, the Fisher esterific. So when I get to it, you need to know all about it, right? You're gonna just whip through that puppy. Okay, tosylation is making a tosylate esters. We'll talk about why we make them. And then the last one is to form an alkoxide and then add a alkyl halide and do an SN2 reaction. You also did that in lab this semester, didn't you? Didn't you do that? Ethoxynaphthalate.
Yes.
Okay, I can't even speak. Okay, I'm pretty sure this one made. Okay, so oxidation, remember, is addition of oxygen, addition of X2 counts also, or loss of H2. That's considered oxidation. Reduction is addition of hydrogen, loss of oxygen, or loss of X2. Okay, so the main ones, your book added in the X2s. I haven't really used that over the world's life, okay, of teaching. But the addition of oxygen, loss of hydrogen, and the addition of hydrogen, loss of oxygen are the two that we really use a lot. Neither, okay, not every reaction is an oxidation reduction, just like every reaction is not SN1, SN2, E1, or E2. Okay, when we did that last semester, everybody wanted to make everything those. Okay, everything is not these either. All right. For example, addition or loss of H plus, OH minus, water, or HX is neither an oxidation nor reduction. It's just an addition or a protonation or a deprotonation. Okay, there's other things besides that. That's only there. Yeah, can we go? Okay. So here is an alkane. An alkane has no bonds to an oxygen, okay? If you convert it to a primary alcohol, no matter how you do it, okay, you get one bond to an O, so you get oxidation. If you lose the two green hydrogens, you get an aldehyde, okay? So we oxidize it further. Okay, if you oxidize it more, you can oxidize aldehydes to carboxylic acid. Okay, if you do that, you added another oxygen. Okay, so you're still, every one of these steps is an oxidation. Okay, do you see that? Okay. This is just a secondary one. You cannot take a ketone and go to a carboxylic acid, because you have two arbs there. You have to have that hydrogen up here in order to go to a carboxylic acid. That's really important. Okay, and if you have a tertiary carbon here, all you can do is make it into an alcohol. You cannot even make that into a ketone, right? Because that carbon, if you put a carbonyl there, how many bonds would that carbon have? Because, oops, because I don't want you to do it. Okay, so look, if you did this, what's wrong with that picture? Yeah, do you see that? Okay, the carbon has 5 bonds. So this is what's going to limit things. Same thing up here. If you took that and you made it into a if you tried to make a carboxylic acid, I'm going to get my thing a little. Anybody think, oh, why don't we just do that? What's wrong with that? We're not just going to give that the black X. We're going to give it the big purple X. Okay, because that carbon has 5 bonds. Okay, don't make carbon have 5. Okay, so we're going to lose hydrogen or gain oxygen. One of the reagents that gets used quite often is chromic acid. It's been used a lot over the years. Chromic acid is H2CrO4. Do you have it?
Yeah, it's very different.
Is it out of order?
Yeah.
I don't know why I did that.
Okay.
Okay, we're with it? Okay. Okay. You can take CrO3, that's oftentimes referred to as chromium trioxide, even though I know that's not the technically correct way to name an inorganic compound, okay? Or you take sodium dichromate and you put them in aqueous H2SO4. When you do that, you make chromic acid in situ. Okay, does that make sense? What's in vivo? Can you use those terms in biology department?
What?
What is in situ? In situ. In situ. Within the reaction mixture. Okay? What's in vivo? Life. Within life. Within the cell. Right? You don't use those over in vivo? Maybe you haven't taken that class yet. Did you, anybody take some on the left? I would think she might use them. I don't know. I never took some. All right, so what we're going to do is we're going to take secondary alcohols to ketones and primary alcohols, y'all, go to aldehydes and then to carboxylic acids. Using this reagent, you cannot stop at the aldehyde. So you know what's going to come, right? The way it is. Okay. All right, now, a couple of things. Chromium is highly colored. Okay, when you do the reaction, your reaction mixture is orange. Okay, when you start. When the reaction is done, the chromium has changed oxidation states and it is now green or blue, depending on how much of it you've got. Okay, but it's kind of green or blue. This can be used as a test to see if it's a primary or secondary alcohol. Okay, what other reaction did I talk about could be used as a test? Because this comes up in these little multiple choice tests that you take at the end. What was the other thing that you could use as a test? Because the color changed. Remember when I talked about bromination and adding bromine to a double bond? Bromine is really dark, red-brown color, and it decolorizes. That gets used as a test for double bonds or triple bonds. This gets used as a test for primary alcohols, secondary alcohols, or aldehydes, because the aldehydes get up. Okay? All right, so here we have a secondary alcohol. The reagents are going to be CrO3 and H2SO4. Okay, and look what we made. A ketone. Here's a primary alcohol. We made a carboxylic acid. I want you to notice that there's the same number of carbon in the starting materials and the products. We do not add a carbon. Okay, all we're doing is pulling away hydrogen. Okay, but what if you wanted the aldehyde? Okay, so there are a couple of exciting ways that have come out over the years to do that. The first one uses pyridinium chlorochromate, which is shortened to PCC. Okay, does anybody know what pyridine is? I feel like this is not showing up good. Maybe I'll have to go to yellow. I don't know. I copied these from another. Okay, here's pyridine. That's pyridine. Pyridinium chlorochromate is basically you protonate it. Okay. And that's your, bless you.
Thank you.
That's your counterion. Okay, that's PCC. BPCC is bipyridinium chlorochromate. Well, bipyridine is simply two of these puppies hooked together. I worked with this one. We were trying to make one that would work and only do one enantiomer. And so we were trying to use nicotine, which has a very similar, there's more, it's different, but it has, you still get this nitrogen there. Okay, so that's the BPCC. You just need to know the letters. Can you do that? Okay, y'all didn't like when I put MCPBA on. Yeah. Okay. These take primary alcohols to aldehydes. They stop at the aldehyde. They don't continue on to the carboxylic acid. When you do the oxidation, you always form that aldehyde. And so what is happening is because you have these pyridine things in there, they are kind of buffering the reaction mixture and they are making it stop. Okay? If you used a secondary alcohol, you would still get a ketone. You would still get a ketone. Okay, so if I did this, and I'll use BPCC, I'm still going to get a ketone. Okay, that doesn't change. So why use that and why not use the other one? Doesn't really matter. But just so you know, chromium is not a good thing for the environment. So we try really hard to not use chromium. And I'm going to show you some things that we've come up with so that we don't have to use chromium. Okay, because you have to handle it carefully. You have to dispose of it carefully. Okay, this one, the PCC came out first. Okay, it came out first, and then they came out with the BPCC one, the bipyridinium one. And what happens is you get byproducts that are solid. So what you can do is you can filter them off. And this one works better than that one as far as getting all of those byproducts out of it. So you get the chromium out right away. You do the reaction, and then you have the solid in there, and then you suction filter it, and you get rid of all of your BPCC. You use a filter aid. Have you heard of diatomaceous earth? Okay, where have you heard of it?
It makes ants move their beds.
Yeah, in nature, right? Yeah. Well, we use it in the lab. What you would do is you would take your butyl funnel and you would put a little bit of that in there, okay, on top of your filter paper, and that helps to catch all of the precipitate gets stuck in the diatomaceous earth, the BPCC precipitates. Okay. Have you ever filtered some and had your filter paper like clog up? You haven't had that happen yet? Okay, it may happen yet. But sometimes you filter stuff and the filter paper clogs up. You can put that diatomaceous earth in there. But if you want the solid, that's an issue. You'd have to get it away from the solid later. Okay, but if you want the filtrate that's coming out, it works really great. Okay, there are also special filters that you can use if you run into that problem. And that's what you want to get is the solid. Okay, so here's our PCC, and we get an aldehyde. Okay. All right, so what is the product from this one? Seven. Okay. Yep, it's B. It's the ketone. Okay. A is just the starting material. Okay. Didn't mean to be tricky. Okay. And this, what would you use to make that? We'll go back. Na2Cr2O7 and H2SO4. What would be the starting material? Here's your clue, CH3. Then what? Then what do we need? CH 2, and then an OH. Okay. Secondary alcohols give ketones. Primary alcohols give carboxylic acids. Okay. Okay. These are some of these other reagents that can be used. One is hypochlorous acid, HOCl. I have not used any of these in my career, okay? But they've all come out. They're all new cool ones, okay? The Collins reagent, they actually throw the pyridine in there and kind of like the PCC thing. Sometimes they'll write Collins reagent or Jones reagent or Swern oxidation on the arrows. So if you're looking at articles, you might run into that, which we will be doing come April. Okay. This is a chromic acid in acetone. That kind of changed a little solubility up on there. This is sodium hypochlorite, NaOCl, in bleach. Okay, so you can actually use bleach to do an oxidation. That's kind of how bleach cleans your clothes. It's oxidizing. Okay, the Swern oxidation, developed by the scientist by the name of Swern. Yeah. DMSO and oxalochloride. Okay, this is oxalochloride. I'm going to write it out this way. Okay. And do you remember what dimethyl sulfoxide is? When did we talk about that? That's DMSO. When did we talk about that? We used it as a special solvent. Polar aprotic solvent, remember? And it helped what kind of reaction? SN. Okay. All right, and a hindered base like triethylamine, the nitrogen has a lone pair, it functions as a base. All right, the Des-Martin periodinane, 1 per iodinane, I don't know, DMP. Mild temperature and neutral pH. Sometimes you might have something in your molecule that will react with acid. So you need to come up, they needed to come up with a method to oxidize stuff so that it wouldn't mess up the other parts of your molecule. And that's where this came into play. Okay, these reagents convert primary alcohols to aldehydes. Okay, what do they convert secondary alcohols to? To what? Ketones. That's all you can get every time. Okay. The big confusing one is primary alcohols. Am I going to get an aldehyde or am I going to get the carboxylic acid? Okay. So any of these will do the aldehyde. Okay. So here's the Swern oxidation. Here's our good old DMSO. Here's our oxalochloride. Okay, here they put the triethylamine right there, and the solvent they used was CH2Cl2. What is that called? 2Cl2. Dichloromethane or methylene chloride. Surely we use this one. Okay, like more than you think. Okay, look what happened. Remember that we're doing an oxidation, so something gets reduced. In this case, the sulfur got reduced. Okay. All right, so what would you get from cyclopentanol, DMSO, COCl2, a triethylamine, CH2Cl2, and minus 60? They do these pretty full. Okay, so this is the Swern. Most of the time, you'll probably see the word Swern. Okay, so what do you get from that? What kind of alcohol is it? Secondary. So we're going to make a ketone. We're not doing the mechanism. Amen. Okay, what about this one? What kind of alcohol is that one? Primary. So what am I going to get? Aldehyde. Okay, which carbon is the one that becomes the aldehyde? The one that the what is attached to? The OH. Because that O is the same O. Okay, they've done a bunch of work to figure that out. Okay, can you see that? Should I go to white? No? Okay. And I'm worried about the white not showing up on the white. I can't win. Okay, this is the DMP. This is one of the new ones. Notice that there's an iodine in here, and look at all the things attached to it. And it has a lone pair on it. It breaks like all those little octet rule things. Okay? Remember, some of the elements will do that. Iodine, chlorine, phosphorus, sulfur. Okay. Well, somebody used that, and look what you make. This is the reduced form. You need to know DMP reagent. I'm not going to ask you to spit out that structure. Okay? Okay, so if I had and I did DMP, okay, what would I get? What kind of alcohol is it? Primary. So what am I going to get? A what? An aldehyde. Can you draw the right one? Okay, notice nothing rearranges. Don't worry about any of that. Woo-hoo. Okay. This shows the chromium reagents, and this shows the chromium-free reagents. They really worked on that because they wanted to avoid, especially if you're doing this on an industrial scale, like big, huge things of it, to make that ketone to then sell to the lab so that they can make something else with that ketone. So they worked on coming up with ways to do this that don't involve chromium, because in the industry, you don't want to have a ton of that chromium and dealing with it. Okay, the other one that would go here would be BPCC. Okay. Okay, so if you want an aldehyde, you can use PCC, BPCC, the SWRN, or the DMP. If you want a carboxylic acid from a primary alcohol, you can use the chromic acid. And the chromic acid reagents, y'all, are CrO3 in H2SO4 or Na2 Cr2O7, sodium dichromate in H2SO4. And having all that acid in there is nasty stuff. Okay, that's how you get carboxylic. Okie dokie. Any questions? I mean, we're not like worrying about the money. It's inorganic. So if you take inorganic, Dr. G can teach you the mechanism if he cares. It wouldn't surprise me if he talked about it again. Okay, so what do you get? The kids used to say, and you all know Dr. Shibuni who left us?
Yeah.
Okay. We were all very sad. He has a job where he doesn't have to drive 4 hours a day. You don't understand why. But yeah, the kids would say, hey, Dr. Shibuni's telling us what you told us in organic isn't always right. I'm like, yep. That's because those are those inorganic elements. They break other rules. We break the organic rules, or the inorganic rules, they break the organic. It's kind of funny. Okay. You ought to get this right. I might cry. Now everyone's scared.
Yeah.
All right, with 17.
We did our best.
All right, what kind of alcohol is this? Tell me about the reagent. It's going to give you what?
I gotta write that.
Oh, I would just like to say I was good.
Yeah, that'd be great.
Okay, why is A wrong?
That's because of
Because somehow you lost carbon. Why is D wrong?
Yep.
If you were going to make D, you would have to start with isopropyl alcohol. This one. Okay. All right, you got to pay attention to that. Okay. Okay. Anybody heard of the breathalyzer test? Anybody take breath? What? Okay. This isn't the way they do it now. Well, when they first came out, they used that chromium reagent. Remember I told you went from orange to green blue? Okay, so what would happen is you would breathe into this thing and the chromium would react with the alcohol in your lungs and it would change colors. And that's how they would know that you had alcohol. Too much alcohol. Okay, now why is it too much alcohol? Are you saying, well, if I just drank a drink, is the alcohol just in my mouth? Okay, no. When you do a breathalyzer test, they're getting the alcohol out of your lungs. Okay, so when you drink alcohol, if you drink too much, what will happen is it will go between the blood-lung barrier and actually come out into your lungs, and that's okay. Okay, to get the actual percentages and stuff, they pretty much have to do a blood test. Okay, so if you think you're close, you might want to insist on. Okay. Yeah, well, we don't want, but you're not drinking and driving, are you? That's right. Just don't drink and drive and you won't have that issue. Okay, the current one now uses a small fuel cell and it catalyzes the oxidation of ethanol by oxygen in air. So it works a little bit different. They don't have to have chromium in there. Okay, the oxidation generates an electric current that is proportional to the amount of ethanol in the sink. So they can kind of get a reasonable idea of how much you have in your bloodstream now. This is newer than the original. The original was the fruit. Okay. Nobody has a car with one of those things that you have to breathe in before they let you start it. You don't want to go there. Don't be doing that. Okay. Features of alcohols and ethers. So where are you now?
Page 2.
Okay, back to page 2. Somehow I moved that all up. Okay, well, I'm not going to worry about it. We all survive. Okay. Alcohols and ethers have groups that are strong bases. Remember that strong bases are poor leading groups. So, for example, if you have, we'll just do this for an example, and you add Cl minus, you may want to do this, okay? But that is not good, all right? Because OH minus is a poor, rotten, crummy, lousy leaving group. I'm trying to make this work, okay? So this does not happen, okay? Okay, strong bases are poor leading groups. Weak bases are good leading groups. Okay, so what we have to do is somehow activate them before they can do substitution or elimination. Okay, so what could you add to methanol so that it would do this reaction? You could add HCl. Okay, why does that work and just adding NaCl not work? Well, what does the H plus do? It reacts with the O to make water, and you now have water as your leading group. Water is a weak base. Agree? Okay. Okay. Sulfonate esters are another way that you can get them to leave, okay? They are made from alcohols. You don't make them from ethers. And they're weakly basic leaving groups, and they will easily undergo substitution reactions, okay? Those get used quite a bit in basic organic synthesis. Okay, so here is a strongly basic leaving group, OH, cannot be displaced by nucleophile. Notice there's this big X right here. There, I made it bigger. Okay, so first we convert it to the alcohol, and then, and let me write it out just so that we get a little protonation practice. How about that? Okay, remember that we're reaching out and grabbing the H plus off. Okay, reach out and grab it. The curved arrow means movement of electrons. It doesn't matter if you don't want it to mean that. That is what the convention is, so we all have to live with it. So if you think, well, the H plus is going there, you got to think of the thing as reaching out and plucking it up. Okay, that's the best way. All right, then we made Br minus. Look at that, all those electrons. And now we come in from the back. Okay, what kind of reaction is that step? SN2. Okay, but there's a protonation step at the beginning. Okay, which now we have a good leaving group. Water, not only is it a weak base, but it's a small neutral molecule. Small neutral molecules are great groups. Okay, airbags. Airbags deploy because there are compounds in there that will give off nitrogen gas. And that's what makes the thing blow up, okay? Nitrogen, N2, small neutral molecule, okay? And I think those molecules that they use in those lose like 3 nitrogens per mole. So it's a huge amount. All right, so what are the organic products for each reaction below? Okay, so what do you think about that first one? Here's your clue. Okay, so what are we going to do? We're going to substitute a what for a what? A bromine for an OH. The byproduct that's formed, I'm only writing it so that if you think about the mechanism, what happens first? The alcohol gets protonated, and then the bromide comes in. Okay, how about the second one? What are we going to do? I seem to be fond of this cyclopentane ring in this chapter. Have you noticed that? Okay, so what am I going to put on my ring? Instead of an OH, I'm going to have an I. What about that one? How you doing drawing the ring? Because that's going to be your clue. Okay, so what do we got? The Cl where the what? Where the OH was. Okay, is that an SN2 mechanism? What kind of alcohol is this? Secondary? Yeah, okay. So what happens first? The OH gets protonated. Then what happens? Does the chloride come in and take out the OH? No, because it's too hindered. So what do we make? A carbocation. What kind of mechanism is this one? Okay, carbocations are flat, so your nucleophiles can come in from either side. Much easier than dealing with that backside attack and all that stuff in the way. We don't want all that stuff in the way. Okay, how'd you do drawing your 7-membered ring? Okay, so now we're going to do this one. Okay, it's not that way. You don't have to draw the 7-membered ring off. Okay, so what am I going to do first? I'm going to grab the H, and then the electrons go to the Br, and you can put all your little lone pairs on there if you want. Okay, so what do I have right now? Oh, look, there's an arrow there. You just can't read it. All right, there's your clue. So what changed? What was the only thing that I changed? I changed from the O to the H, right? Okay, so is that methyl group still there? Yeah. Is that bond to the O still there? Yeah. So don't make more happen than what actually happened, whatever you drew the arrows for. Okay, so here's my OH, and now I have it bonded to an H. And what can you tell me about that O? It is now positive. Are you positive? Okay, and what else did I make? Br what? Minus. Okay. I feel like I can't read that. All right, now what happens? The water leaves. How do you show that with the arrow? Yes, that bond is going to the O. Okay, so there's 2 electrons in that bond. They go to the O, and the O now has 2 what? Lone pairs. What about the carbon that it was bonded to begin with? What does it have? A positive charge. Okay, and then we made H2O. Okay, sometimes when we have stick pictures, people have a hard time remembering where the hydrogens are. Okay, you have a hard time with that because you're drawing 5 bonded carbons and you didn't even notice because the hydrogen is there. Okay, you need to draw them in. Okay, so just letting you know. There is no hydrogen on this carbon, right? Right? Okay, okay. All right, hang on. Here for Valentine's. Okay, so this goes there. Negative to positive. Okay. So now what do we make? In 3 easy steps. Okay, and we have H2O. I'll just put it down there. Okay. Okay, how many steps was there? 3. Okay, so if you're going to draw your reaction coordinate diagram, how many mountains should you have? 3. Okay, which one is the tallest? What do you think? Which one do you think is the tallest mountain? Well, in other words, which step is the slowest step? It's the second one. It's the second one. Protonation is fast, okay? Negative to positive is fast, okay? This is your rate determining step. So that will be the high point in your mountain range, okay? Okay, here's a primary alcohol. So let's do it. So how do we do that one? What do we do first? Grab the H. Reach out and grab the H. And what happens to the electrons in the HCl bond? We go to the Cl. Okay, so now what do we have? This is what didn't change. All that's going to change is where I drew the arrows. Okay, so that O that had 2 lone pairs, now what does it have? It has an H, it's positive, and it only has 1 lone pair. And what else did I get? Cl who? Minus, okay? So what does that do? What happens now? Do we lose water? We lose water, what kind of carbocation do I make? Primary. Our primary one's stable. So now we're going to do the backside attack there. I drew those electrons in there. Okay, so you're going to get is it 3? Okay, plus H2O. The O now has 2 lone pairs on it. Okay. Any questions? What if you're sick? That's the issue. Okay. Typically, the secondary carbocations are stable enough that you can get them. And so we can go SN1. Okay. The big thing is to worry about is if there is a chirality. Okay. Because if this was a chiral center, like instead of having CH2, we had a CH and a D. What's D? Deuterium. Okay, now all of a sudden we have a chiral center. When you do an SN2 reaction, what happens to the chirality? It gets flipped, inverted. Okay, so just bringing it all back, I'm telling you. Okay? Okay, a lot of times when you react with primary alcohols, the reaction is so slow that we add a catalyst. This is what you'll see, zinc chloride being added. Okay, zinc chloride is a Lewis acid. We have not used that term very much yet. What is a Lewis acid? It is an electron pair acceptor. Okay, remember when you have to draw Lewis structures, you have to show all the electrons. How you know the Lewis acid-base definition has to do with the electrons. The Bronsted-Lowry acid-base definition has to do with what? Protons. H plus, right? Okay. Okay, it complexes with the lone pair electrons on the oxygen, weakening the CO bond. Okay, this is the basis of a test for alcohols called the Lucas test. Okay, so what you do is you mix the Lucas reagent, which is concentrated HCl and zinc chloride, okay, and an insoluble layer forms. That insoluble layer is your acid chloride, okay? Did you do an SN1 reaction where you took T-butyl alcohol and you added concentrated HCl and you shook it in your step funnel? You remember doing that? Okay. That extra layer that shows on the top is RCl. It's your alkyl halide. Okay. And a tertiary alcohol reacts quickly. You only shook it for what? 15 minutes, right? Okay. A secondary takes 5 to 10 minutes and a primary takes heating and much longer. You can decide if it's a primary, secondary, tertiary alcohol using that test. You watch for that insoluble layer to form. It's not as dramatic as the chromium test or the bromine test, but you do get an insoluble layer. Okay? Limitations. You can't do it on every alcohol because they're not always soluble in the which is kind of a bummer. All right, study up. I'll see you on Monday. Monday.
Next month, Friday.
Okay. Yeah, just print out like. Okay, that'll work.